Hello, and thanks for using TickBoom, a free service that helps high school students with their math problems. In this video, I'll be answering question 6 of the Board of Studies Extension 2 trial paper from 2020. And it's a continuation of a series where I'm working through this paper systematically from question 1 all the way through to question 16. Here in question 6, we're told that the vector equation of a line in three-dimensional space for some scalar lambda is given by r vector equals a vector plus lambda n hat vector. And in this case, a vector is the position vector, and n hat vector is the unit vector in the direction of the line. We're told to let p vector be some point which does not lie on the line, and then we're asked which of the following represents the shortest distance from p hat to the line, and we're given 4 options as normal, all involving the magnitude of some expression. Now, these vector questions can be quite difficult, particularly the three-dimensional ones, because they can be harder to visualize. But I'll have a crack at kind of working through this. If you do find my explanation helpful, please be sure to give it a like. And if you're someone who wants to keep their finger on the pulse with the kinds of questions other students are struggling with, be sure to subscribe to my channel so that you can stay in the loop. Now, to kick things off, what I've done is I've written up the vector line that we're given and just written out kind of what we're dealing with. So we're looking for the shortest distance from some vector p to our vector line r, and we're given these 4 options. Now, often the best place to start with vector questions is to draw up a diagram. The difficulty with three-dimensional vectors is it can be hard to draw a diagram that captures that three-dimensional element. And to try and explain that, I've actually got a few props. I've got a pacer lead, which was the best thing I could find to represent a straight line. And then I've got a pacer eraser, which was the best thing I could find to represent a point. Now, in terms of the vector line, which in this case is r, essentially we're probably used to seeing the vector kind of in 2 dimensions. Like on this flat page, we'll have some point where it starts in the x-plane and then the y-plane, and then, you know, it'll have some kind of direction. And that's kind of what we're used to. Now, where it gets tricky in 3 dimensions is you'll still kind of go, where's my x? Where's my y? But then you also come off the page into the 3rd dimension, and from there you can kind of have a direction that kind of can go anywhere. So if I just pick, you know, this as my vector line, and it happens to have kind of whatever angle it does, we're told that there's some point P, which again can be anywhere. It's not on the line, but it could be below it, above it, on this side, who knows. And we're basically asked what's the shortest distance from this point P to this vector line. And hopefully instinctively you know that the shortest distance, it's going to be a straight line perpendicular to the vector, because you're not going to kind of go this way or this way. The shortest distance between 2 points is the perpendicular straight line. But it would be quite hard to draw a 3D diagram to capture all that. So what I'll do, I might put these aside. I'm just going to draw a diagram in 2 dimensions, and you just have to appreciate that this is all happening in 3 dimensions. But I think it is still possible to kind of grapple with what we're dealing with, even though my diagram won't be a kind of 3-dimensional work of art. So what I might do to start, I'll just draw some line. We'll call this line, this is the vector line r, which is given here. Now, if I just pick some point, arbitrary point here, I'll call it O. This is our origin point. And we know that the position vector, a vector, must lie on this line. So I can kind of pick any point, let's just put it here. I might call it point A. And I know that the vector from the origin to that point, which in our case will be a vector, kind of lies on this line. Now we're also told that there's some other point P, or there's a vector. I might just pick any point. It doesn't really matter where it is as long as it's not on this line. So I might just put it, say, here. I'll call it point P. And the vector to point P, so from O to P, that's vector P. And the question is asking us what's the expression that will give us the shortest distance from this point P to this line. So what I might do is I'll just maybe we want it to be at right angles. So basically this dashed line represents the distance between this point P, this vector P, and this line vector R. So I might just call that point, just for the sake of kind of identifying it, I'll call it point X. So in essence, we want the distance between P and X, because if this is perpendicular, this will be the shortest distance between the point and the line. So what I might write is, to start, we'll say the shortest distance from vector P to the line vector R is basically the magnitude of this vector Px. So in theory, if we can get an expression for vector Px, then the magnitude of that expression will give us the shortest distance, and hopefully that expression is one of the options we see here. So in terms of what is Px, I think one way we can start in terms of going from P to X, one way we can do that is we could go from P to A, this vector here, and then we could go from A to X, this vector here. So let's write that. So we know that the vector Px is equal to the vector Pa plus the vector Ax. So now if we can get an expression for vector Pa and an expression for vector Ax, I think we'll be well on our way. Now vector Pa, hopefully you can see, to get from P to A, we can go from P to O and then O to A. So in terms of our notation, going from P to O would be the same magnitude as vector P, but the opposite direction. So that'll be negative P vector plus A vector. So I'll just write that as A vector minus P vector. And I think that's good news because we see A vector minus P vector in all of our options. So we know we're on the right track here. The next thing to do is to think about Ax vector and what an expression for that might be. Now, if you know your vector rules, one thing you'll know is that the vector A to X is actually, in theory, the projection of vector AP onto this line vector R. And that's because this point X is perpendicular to the point P. So if we can get the expression for the projection of vector AP onto the line R, then we'll have this vector AX, and then we'll be well on our way to getting the expression for what we need. So I might have to turn over here just for space, but what I'll do is I'll write this vector AX that we're dealing with. So just to remind you, this vector here is the projection of the vector AP, and notice the direction here is important. It's this vector from A to P onto the line vector R. So in general, the rule for what is the projection of a vector onto another line vector is equal to, and I'll just write in brackets, it's the line vector, or it's the dot product of the line vector and the vector that we're dealing with. Now, the vector AP Now we've just worked out PA is A vector minus P vector. So AP is just the same magnitude, opposite directions. So it's the dot product of R vector times negative A vector minus P vector divided by the dot product of R vector times itself, and all of that times the R vector. So that's just the generic formula for the projection of a vector onto a line vector. Now what we can do here is we can kind of start to simplify this. I might just bring this negative out. And we'll get the R vector dot product with A vector minus P vector. And this R vector dot R vector, I can just write as the magnitude of R vector squared times R vector. And the reason I can do that is because by definition, the dot product of a vector times itself is the magnitude of that vector squared. So in continuing to simplify this, I'll write this as negative, and this R vector, magnitude of R vector squared, I might just separate that out into two things. So we'll have R vector on the magnitude of R vector times the dot product of A vector minus P vector, and then times R vector divided by the other magnitude of R vector. And the reason I've done that is because this is the definition, R vector on the magnitude of R vector is the definition of the unit vector in the direction of R. So that now I can write as negative bracket, and this R vector on the magnitude of R vector, it's the unit vector of R, which you may remember in our case is denoted with n hat vector. That is the unit vector for R. So I'll replace these with n hat vector dot product A vector minus P vector all times n hat vector. And again, that's good news because that's quite similar to kind of what all of our options had in them. So now we need to kind of just do a bit of rearranging. But let's kind of now put this all together. So therefore, the magnitude of px vector, which is what we're concerned with, is equal to the magnitude of PA vector plus AX vector. So PA vector plus AX vector, which equals the magnitude, and PA vector we saw was A vector minus P vector, and AX vector we've just worked out as minus n hat vector dot A vector minus P vector bracket n hat vector. So it's that magnitude. Now that's very close to this option here, but notice the dot products are reversed, but that's okay. They're easy to, they can be written in any order. But notice that this bit is written before this bit. So it's as if we've had a negative in there. So it's equal to the magnitude of negative, and then we kind of get, I'll just write it here, negative bracket, and then we write this n hat, or actually I might write this, maybe I'll scrap this, equals the magnitude of negative bracket, I might write this first because that's just the order that all the answers are in. So A vector minus P vector dot product n hat vector times n hat vector. I'm just trying to be very careful with my brackets. And then because I've done a negative, I'll have to do a negative here, minus A vector minus P vector. And it's the magnitude of that. So that will give us negative of all this plus this, which is what we started with. Now, the reason that's helpful is because we're dealing with magnitude here. So whether it's the magnitude of the positive or negative version of something, and maybe I have to do one more bracket there. So that bracket is closed by that bracket. Yep. I can now just drop off that negative because we're dealing with magnitude, or if it helps, you could think of it as absolute value. So therefore I can write that as the magnitude of, and now we can just write a vector minus p vector dot n hat vector, and they need brackets, n hat vector minus a vector minus p vector. I wonder, so that bracket is closed with that. So actually I do need another bracket here. So that bracket matches that bracket matches that, and that, yeah, okay. Got to be very careful with your brackets here. There's brackets flying around, but hopefully I haven't blundered that. But ultimately what we've just got to there is expression C, a vector minus p vector dot n hat vector, all of that times n hat vector minus a vector minus p vector. So that's it. Our answer is C.
Panic boom!
So yeah, that's how you deal with that question. As I mentioned at the beginning, these 3D vector questions can kind of mess with your head in a way because it's quite hard to visualize what's happening in 3 dimensions. But in the end, I was able to kind of still represent graphically what we were dealing with, even though I was just kind of putting it all in 2 dimensions. We still got to the right place. You just kind of always have to have in the back of your head that all these lines I'm drawing could actually be moving around in 3 dimensions in theory. But at the end of the day, a lot of the concepts and the rules, like in particular this rule, whether it's a 2-dimensional vector or 3-dimensional vector, it's the same rule anyway, so you're still going to get to the right place. So hopefully you've been able to follow all that. I think it was definitely a tricky one, probably the hardest question of this exam so far. So hopefully you were able to follow along, and tick boom.